I swear all I do is sit here thinking of cheesy jokes. But our linear relations linear models video starts with perhaps the cheesiest. What on earth is a linear model? Is it a model that lies down? I don't know, there's a mental image of a model lying down. Whew. But no, maybe not. So, our linear model. What is a linear model? Well, I suppose it's time for that all-important, let's see what actually happens with regards to our important language. By the end of this video, hopefully you'll understand a little bit about what a cost function is. You'll understand how we can relate or use equations of straight lines, and perhaps the idea of what linear means. So what is a linear model? Well, as we've already said, we can see before that we have a straight line, can have equation of y equals mx plus c, and so y equals 3x minus 2 can be written in the gradient form, or if we wanted to write y minus 3x equals negative 2 in our intercept form, these could mean all sorts of different things. But what if I was to change letters? What if I was to say, oh, I don't know, c equals 36 plus 10n? What does that actually mean? Well, it's still an equation of a straight line, because if we write underneath it the idea of y equals mx plus c, yep, it's written in a different way because maths is trying to trick you. But I still have a straight line here. I have a letter, I have a different letter, and I have a number. So what could this actually stand for? Well, I don't know, the cost of nanas is equal to 36, some sort of random, well, hold on a moment, 36 plus 10 times the number of nanas I have. Well, if I'm going to walk into a shop, that would sort of be like walking into Coles and, for example, picking up 5 nanas and then having to pay, well, actually, let's work that out. If I had the number of nanas equals 5, and I have the equation c equals 36 plus 10 times n, which would give me 36 plus 10 times 5, which is equal to 36 plus 50, or 86. What I'm trying to say, or what that suggests now, is that for 5 nanas, I'm going to end up paying 86, let's say, dollars. Why am I paying 36? What am I paying this 36 for? What's all on there? Am I paying that to walk into the store, say hello? Is that the cost of the person it's taking to scan and weigh my nanas? Who on earth would ever pay a fee for something that they've not actually used yet? Well, believe it or not, later on there is an example of exactly that. Something whereby you pay before you even actually go anywhere. Maybe that's a bit of a hint. So this equation can actually stand for a real-life model and a real-life linear model. Just a word of further learning, or just to recap if you've done this before. If you notice, when we write y equals mx plus c, this actually could be done in an equation, can be done in a graph, whereby, well, what is the y-axis called? Well, the y is under the c, so that would mean that the c would actually go there. I can label my y-axis using a c, because that's where my formula says. Well, where's the x lie? Well, the x in this case is called n. So, yep, I can actually do n on the bottom. And what would this 36 mean? Well, hopefully that would be the start point or the y-intercept on my graph. And I'm not going to draw the actual line on, but because it's got a plus 10, we know that it's pretty much going to be something along those lines. So these letters in place of the y and the x can actually be written on my axes in terms of the y and the x. And there is actually an order in which you write these as well, because this n here means the thing I change. So when I walk into Coles, I could order any number of nanas, and the cost of those nanas are actually dependent on the number of nanas I buy. So the thing that depends on actually goes on the y-axis, but that's a little bit of just pre-learning, post-learning, or just something to let you know. So how does this relate to a real-world example? Well, after a long day thinking about maths in the park, Ethan decided it was time to head home. He chose to take a cab which charges a flag fall of $3.50 and 25 cents for each kilometre travelled home. Write a cost function for his trip. What on earth is this flag fall? Well, that's exactly what I was talking about a moment ago. When you get into a cab, before you even leave, the cab will charge you $3.50. Theoretically speaking, you could walk into the cab and walk out again without going anywhere, and you would owe that cab driver $3.50. Whoa! So my initial cost, the initial cost of that cab before I actually do anything, is $3.50. He then charges me 25 cents for each kilometre. So, I don't know, let's talk about my initial cost or my flag fall now as being F. And we're not going to write in dollars, let's write it as 3.5. So we've now got kilometres. I'm going to be charged 25 cents for every kilometre. If I travel 1 kilometre, I'll have 25 cents, 2 kilometres, 50 cents, 10 kilometres, $2.50. So can I write that in a way that is a bit of a formula? Well, yes. If we let K equals the number of kilometres, then we know that using the maths we've just done in our head, that we would then do the number of kilometres times 25 cents. But there's a small trick in this question. Of course there's a trick in the question, because if you think about it, the initial flag fall was done in dollars and our kilometres was charged in cents. So I reckon we should actually rewrite this in the terms of K times 0.25. We need to make sure that we actually get that in the right way. We normally put the numbers first, so let's just change that to 0.25K. So can we now write a formula for the cost of my cab journey for different lengths? Well, we need one more variable then, or we need something else. So we've obviously said cost, so let's have the letter C to stand for cost. So now let's go back to the real world example. I know the cost of my cab is equal to this flag fall. I've got to pay $3.50 plus what he then charges me for every single kilometre then on. Whoa, hold on a moment, that looks suspiciously familiar. Well, it is. Firstly, this thing here, because we like to call things complicated things in Australia, this thing here is called the cost function. Right? It is the cost function. It basically is a equation or a formula to help me work out the cost of my cab charge. And the cost is given by $3.50, my flag fall, which I pay regardless of how far I go, plus 25 cents per kilometre. Does that fit my y equals mx plus c? Well, of course it does. Y equals, that must be my gradient, that must be my x, plus c. Wow. I've now made a linear model. This thing here is my linear model. Could I now go on and actually plot that on a graph? Yep, I could plot that on a graph, slightly beyond the idea of this, but you know, if you know what the intercept is and you know what the gradient is, you know what the axes are called, in this case C and K, you can draw a graph quite easily. So there are various things that you end up paying before you even use it, and cabs are one of the great examples. Unfortunately, I am devastated. Beyond my best will to join a gym, I have found myself once again addicted to Kentucky Fried Chicken. Yes, those twisters, those hot spicy wings call to me every evening, and I am there alone on Swanson Street, gorging myself on a bargain bucket. Life is bad. However, I've decided that I need to try and work out that if I continue this, how much longer it will be before I am absolutely huge. What will I weigh on day 27 if I continue my rampant eating? So, well, I'm afraid I've lost half the information. I don't actually know what I weighed on day 1, 2, 3 or 4, and I need to try and find what am I going to weigh on day 27. Alright? Well, surely there must be a way of doing this. Well, actually there is. I use the idea of y equals mx plus c. We know that this has got something to do with a straight line. It tells me in the question. But how do I find my equation to then help me find day 27? Well, let's see. Hold on a moment. These values on the top of a table generally stand for my x coordinate. So the top of my table generally stands for my x values. And the bottom generally stand for the y values. So, hold on a moment. I now know that weight can be written by W. So let's have weight as W. And let's have day as little d. That seems to make sense. So I now know what my axes have got on them, W and D, but I need to find M and I need to find C. Well, they're not actually giving me any coordinates, are they? Of course they're giving me coordinates. They're just doing it once again in a completely different way. Look, if this top value is equal to my x values and this bottom is equal to my y, so the table is just another way of giving me coordinates. We've got 4,72, 5,73, 6,74, and 7,75. Right, okay, so how does that help us? Well, I only need two coordinates. Remember, to find a gradient, you only need to use two coordinates. So let's move over here and let's choose, I don't know, the first and the last. I've got 4,72 and I've got 7,75. Ooh. Right, so m is equal to rise over run, or more importantly, the difference in y coordinates. So 75 minus 72 divided by 7 minus 4. Well, 75 minus 72 is 3, and 7 minus 4 is 3, so my gradient works out to be 1. There you go, gradient is equal to 1. How do I find my c value? Exactly the same as we did the last time. I've got y equals mx plus c. I now know my gradient is 1. Do I have an x and a y value? Well, of course, I've actually now got 1, 2, 3, 4. I can use any of these because they fall on the line, but we use 4 and 72. So we know that y is 72. I know that x is 4, and I'm wanting to find c. So 72 is equal to 4 plus c. C is equal to 72 minus 4, or c is equal to 68. So I can now express my general equation of the line as y equals m, which is 1, times x plus 68, or y equals x plus 68, because the x is equal to 1x is equal to x. Right, well, that now applies to the equation we first started with, because the same thing, right? All we've done is we've used this table to find a general equation of y equals mx plus c. This equation down the bottom here, this y equals x plus 68, is this equation here. So y equals x plus 68 is exactly the same. I may change the letters, but what was the value of m? M was 1. What was the value of c? Plus 68. So I can now write my equation that my weight is equal to the number of days plus 68. There you go. That is my linear model. Then I'll repeat again. The weight that I'm going to be is equal to the number of days plus 68. Well, if I now want to go back to my original question and find my weight on day 27, well, what do? I now know that if I'm on day 27, d is equal to 27, so w will become equal to 27 plus 68, which is equal to 95. Woo! I'm going to be 95 kilos on day 27 if I keep hitting the KFC machine, so maybe I will renew my gym membership and start that treadmill. Again, a really easy example, and partly I suppose people will say, yeah, but you could actually have worked that out. Yes, you could have done, but remember this lesson is about the process. Doesn't matter what the values are, it's talking about the fact that these things are coordinates. You can come up with the equation just using tables, and you can just use two coordinates from any table to help you find the general equation that you then put back into your equation that you are trying to create. Last example. An initially empty swimming pool is being filled with cola at a rate of 10 litres per minute. Write a rule for the volume V litres of cola in the swimming pool at time t minutes after the filling of the swimming pool starts. Right, so they want a rule for V litres. They are basically saying in code, we want a rule that starts with V equals. It's telling us that it's being filled at a rate of 10 litres per minute. What does that actually mean? 10 litres per minute. 10 litres per minute. It means that in every single minute it's having 10 litres added to it. So every minute I'm filling this thing, it's going to be 10 litres bigger. So if I call my minutes the letter M, that means every minute I'm going to have 10m more litres. Okay, so I want a formula that starts V equals. I know this is linear, so it's got to have something about y equals mx plus c. Well, they've told me that we want a formula beginning with volume equals. We now know that actually this mx business is actually going to be 10m because it's 10 minutes or 10 litres per minute. But what is this c? What does this c stand for? What is my flag for? What is my what was the beginning condition? And actually that c can stand for what we call in VCE my initial condition. What did we start at? Well, with the cab, our initial condition was we paid $3.50 the second we got into the cab regardless. What was our previous example? Gaining weight. Well, we didn't know what my start weight was initially, but our formula seemed to suggest that actually my initial weight on day 0 was 68 kilos. They were my initial figures. Let's just check that. Let's just make sure. Yep, there we go. My initial weight was 68 kilos. Right, on day 0, if I'd gone this back, or day 1, no, in fact on day 0, if I'd gone back, I'd have found out that my weight was 68 kilos. So that initial value is my initial conditions. So let's go back to my question. Oh, hold on, an initially empty swimming pool. So if it's initially empty, I would suggest then that C equals 0. And so I have that my volume is equal to 10 times M, which is otherwise known as the volume is equal to 10 times the number of minutes I'm filling my swimming pool with. Look, another trivial example, but again, the general idea. That reaches the end of this video. Hope you've learned something new.